Hello again, class. This will be the third video and the final one for recorded lectures of section 3.2, right triangle trigonometry functions. And so what we're going to do in this section is to do some applications. As an electrical engineer, I didn't measure distance very often, but one of the things that trig functions do for us is give us this really cool way to be able to estimate or even get a very accurate measurement of distance given a distance of just one side, and then if you know the angle. And so we're going to look at two different applications. One example would be you would be standing on the ground and you would be looking up to an object and you want to estimate what the height is given a length and an angle. And another one would be, say, like you're in a plane and you're looking down, and that would call the angle of depression. And you want to figure out how far you are from where you are in the plane, the observer, all the way down to the object here. So the observer here is the angle of elevation, here is the angle of depression. And so one of the strategies is, say, if we get this problem here. Here you're trying to figure out how tall the Washington Monument is. And what you've done is you've measured the distance from where you stand to the bottom of the Washington Monument. And that is 115 feet. And you see that the angle from where you're at to the top of the Washington Monument is 78.3 degrees. So what I like to do when I do these problems, sorry about that, I put that at the whiteboard, is to generate a sketch of it. And so it's nice here because in the book it had a nice sketch. So you're standing right here. And so this angle here is 78.3 degrees. And this distance here is 115 feet. And the height of the Washington Monument is what we're trying to calculate. I'm just going to use y for that calculation. So remember, this is the angle. Remember, we used theta for angle. So if this is the angle, this is adjacent, right? That's the adjacent side. This is the opposite side. And this is the hypotenuse. So the question always is, what is the best trig function to use for this calculation? So when you have an equation, ideally, if you have a single equation to solve it, you would need just one unknown with regard to that. So what we don't know is we don't know what the hypotenuse is, right? And so with regard to that, we don't need to calculate the hypotenuse. So we won't need to use sine or cosine, because remember, sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So the one that we want to use is tangent. And remember, tan of theta is opposite over adjacent. So in this calculation, we have two of the three, and so we could do the calculation, a little bit of algebra, and finish it. So what we have here is tan of the angle, which is 78.3 degrees. And then we have opposite, which is the height we're looking for, which is y, and adjacent is our 115 feet. So when you do a little bit of algebra, bring the 115 to the other side, you get y equals tan of 78.3 degrees times 115 feet. So if you get out your calculator and do tan of 78.3, I get 4.8 say 29, just round a little bit, times 115 feet. And so when you do that calculation, let's round just to the nearest, you would get 555, let's say to the 10th degree feet. So that gives you a really good estimate of what the height would be using some trig functions. Again, for those of you thinking about architecture, trig is very, very handy for that, for a lot of these measurements. Even if you're a builder, right? It's nice to understand some, you don't need the super complicated part of trig, but this idea of being able to do some measurements is really quite useful. And so I have this in the slides as well, where we do the calculation. And again, here I rounded just to the feet and not tenth of feet with regards to that. So let's take a look at this next one. And this one is a little bit more complicated. And so this one gives us, this is the elevation again, where we're trying to figure out the height of this flagpole. And so you can see we have two angles. From the top of the building, it's 24 degrees. And from where we're at to the flagpole is 27 degrees. So what is the strategy here? Well, the strategy would be calculate the height of the building, then calculate not only the height of the building, but the height of the building with the flagpole, and then subtract the two. And that's how we would get the height of the flagpole. So again, I keep hitting the wrong button. Sorry about that. So now we're going to do this calculation on the whiteboard. So again, we have the building, right? And we have the flagpole. And so we define this as H, and up to the flagpole as K. And then we have, this is 500 feet. This angle is 24 degrees. And then the angle to the flagpole is 27 degrees. It's kind of a messy drawing, but it really has everything we need to do this calculation. So again, how do we calculate H? Well, remember this again, these are the angles. So this is the adjacent. And again, this side is the opposite. And this here is our hypotenuse again. So again, we're using tangent. Tangent seems to be the one of choice here. And so again, to calculate H, we would have tan of the smaller angle, 24 degrees, equals opposite, which is H, over hypotenuse, which is 500 feet. So when you do that calculation, you would have tan of 24 degrees times 500 feet. So again, you need a calculator. And on my iPhone, those calculators are available as well with regards to that. So when you plug that into the calculator, let me tell you what, let's see here. So 24 tan is 0.445. So that would be 0.445 times 500 feet. And if we round to the nearest foot, you end up with 223 feet. And so how do we get K? Well, we now, instead of 27 degrees or 24 degrees, we have 27 degrees. And so we have opposite, which is K now, over 500 feet. So you can kind of see a pattern here, right? So K would be tan of 27 degrees times 500 feet. So when you do 27 and tan, it should be a little bit bigger number, right? It's 0.509 times 500 feet. And so when you do that calculation, you get approximately 255 feet. So the flagpole here is K, which is the total, minus H, which is just the building. So it would be K minus H is the flagpole height. And that would be 255 feet minus 223 feet. If I did my arithmetic right, you would have 32 feet for the height of the flagpole. So a couple applications here. I'm going to do one more, but here, let me hit the right button this time. So again, I have these calculations done and the presentation as well. So the last one that I'm going to do is a little drink there, is actually problem 48 in your textbook. I thought, okay, let's just pick one right out of there and see what it looks like here. So if you take a look at this one before I show you the answers, this is, we're going to estimate this Gateway Arch, which is in St. Louis. It's really cool. Been on top of the Gateway Arch. If you ever get to St. Louis, it's definitely worth it. So here we're going to do the idea now that we're doing the depression angle, right? If we're a pilot and wants to estimate the distance. So basically what this says is that at an elevation of 35,000 feet, the pilot would like to estimate her distance from the Gateway Arch. She finds that the angle of depression to the point on the ground below the arch is 22 degrees. So if you take a look at how we would sketch this, and this is a very, I find it a challenge trying to sketch it. And so when we do this sketch, what we would recommend here is clear this one. And my one of the reasons why I became an electrical engineer is I barely passed my drafting class. So you can tell I'm not a very good drawer, but here's my plane, right? So my plane is going, and let's say this is the arch down here. And so that would be the arch. So what this is talking about is that the angle of depression would look like this. Point at the bottom of the arch, right? And so now what we have is this, which is 22 degrees. So that is the angle of depression. And so what this says is that there's an elevation of 35,000 feet. So that means this is the ground, right? So the plane is 35,000 feet. And if the plane's 35,000 feet, if when it gets right on top of it, it's still going to be 35,000 feet. So that's where this comes in. It's a little bit tricky with regards to that. So the idea is that the pilot wants to know what's the distance between the plane and the arch. So the idea here is, here's our angle, right? So this would be adjacent. This would be opposite. And here's our hypotenuse right here, right? So what are we trying to calculate in this case? We're trying to calculate the hypotenuse, the distance from the plane all the way down to the bottom of the arch. So in this case, we're going to use sine. So we have sine of 22 degrees, which would equal opposite, which is 35,000, divided by the hypotenuse is what we're trying to calculate. So doing a little bit of algebra, we'll flip-flop this, and the hypotenuse will equal 35,000 divided by sine of 22 degrees. So what is sine of 22 degrees? I get 0.375. So hypotenuse of 35,000 feet divided by 0.375. And say like we round to the nearest foot, you would end up with 9,000 or 93,431. So again, the architects in the room, which we're not in the room, unfortunately, these types of calculations will end up being very useful with regard to that. Mechanical engineers as well. As an electrical engineer, there's some other aspects of trig that I use quite a bit, which we'll be talking about actually pretty shortly, so that'll be kind of cool. So that ends the recorded lectures for section 3.2, and I'll get on to 3.3 next. Have a great day.